Let us have a quick recap of what we have seen so far. We were having a continuous time signal x of t, and we have tried to sample that signal at some instances in order to obtain the samples of those signals. Those samples can be obtained by having a train of impulses, that signal that we have indicated by p of t, and if we multiply x of t with p of t, we are going to get the sampled version of the signal, that is xp of t, which is going to be a scaled version of these impulses, with the scaling factor being x of n t. That means the value that is present at that instance. In the Fourier domain, if the original signal is having the spectrum something like this, the sampled version of the signal will have the same spectrum or the same Fourier transform, but being replicated at the integer multiple of this sampling frequency. And we have also seen that in order to recover back the original signal, we must pass the output, that means xp of omega, through a filter that will retain the middle component and will simply ignore the rest of the components. We have seen that, and the cutoff frequency of this filter, so the cutoff frequency of this filter, omega c, must be between this omega m and omega s minus omega m. This we have already seen. So we have this cutoff frequency omega c that must be between this omega m and omega s minus omega m. Now let's have a look at the time domain representation of this reconstructed signal. What I mean by that is we are having the samples. Now still the question remains how these samples are getting reconstructed back in the time domain. Although it is clear in the Fourier domain that we must have a filter such that it would retain the middle component and should ignore the rest, but how it would reconstruct the original signal, that is the continuous signal, from its samples? That's a question that we should ask now. We have already seen the Fourier domain or the frequency domain perspective. Now we are going to see the time domain perspective of the reconstruction of the signal. Now for that, we must see that this filter that we are going to consider is having the shape something like this. And in order to see the time domain equivalent, we must obtain the impulse response of this filter, or the time domain representation of this filter. As we can see here, in order to recover back the original signal, we must multiply the spectrum of xp of omega with the spectrum or the filter that we have named here as h of omega. In that sense, in time domain, we need to convolve xp of t with the equivalent time domain expression for this filter. We know from the properties of Fourier transform that in Fourier domain, if we are multiplying into signals, in time domain it is getting convolved. So now we know what is xp of t, that means the time domain representation of xp of omega. We have it here, but we don't know the inverse Fourier of h of omega, that means the filter here. So let's try to find out the time domain representation of this filter, and once we know that, we can simply convolve the time domain representation of x of omega, xp of omega, and the time domain representation of h of omega in order to obtain the reconstructed signal. So let's do that. So let me put what we have said so far. The xp of t, that means the sampled version of the signal, is simply x of t times p of t. In Fourier domain, it is xp of omega, and due to the properties, it is going to be the convolution between these two. So it is going to be convolution between x of omega and p of omega with a scaling factor of 2 pi there. This we have already seen. Now we need to recover back the original signal. That means the original signal, let that be the recovered signal, let it be xr of t. We need to recover back this signal xr of t. So let the recovered signal, let it be xr of t, whose Fourier transform is indicated by, let's say, xr of omega. What is this? This is the recovered signal, let that be xr of t, that means the reconstructed signal, and let xr of omega be the Fourier transform of this recovered signal. Now as we can see from the Fourier domain's perspective, that if you want to recover back xr of omega, this is equivalent to say that we must multiply the spectrum of x p of omega with h of omega, where this h of omega is the filter response. This is the filter, and this one here is the sample signal. So xp of omega is the Fourier transform of the sample signal, h of omega is the Fourier transform of the filter itself. So if we multiply these two, we are going to have this reconstructed signal Fourier transform. And if we need to look into the time domain perspective of this, it is simply going to be x r of t the reconstruction signal is going to be simply the convolution between x p of t and h of t. Now this h of t is simply the time domain representation of this filter, or the inverse Fourier transform of the filter h of omega that we have defined in the Fourier domain. Now that is what we are going to see in this module, how this xr of t is getting reconstructed in the time domain. That's what we are going to see. What is h of t? H of t is simply the inverse Fourier transform of the filter. So there is a relation of this h of t being the Fourier transform of h of omega, that is the filter. Now we know h of omega, how it looks like. We don't know how h of t is going to be. So let's try to calculate the inverse Fourier transform of this h of omega. We know what is h of omega. H of omega is the filter that we should construct with a cutoff frequency of omega c. Of course, this omega c between omega m and omega s minus omega m. And this filter h of omega, we need to find this h of t. Now this h of t can be obtained by having the inverse Fourier transform of this h of omega. So this inverse Fourier transform of h of omega is given by, so h of t is given by the inverse Fourier transform definition. We know that it is 1 upon 2 pi integration from minus infinite to infinite h of omega e power j omega t d omega. Now we know what is h of omega here. H of omega is constant as t between this omega c, minus omega c and omega c. So this is minus omega c here and omega c there. So it is constant as t between omega c, minus omega c and omega c, and it is 0 otherwise. So this integration is going to be between, so this is going to be equals to 1 upon 2 pi integration from minus omega c to omega c. H of omega is constant and otherwise it is 0, e power j omega t d omega, and this is going to be equals to 1 upon t upon 2 pi. Just because t is constant, I can take it outside. It's going to be e power, so integration is going to be 1 upon jt, just because the variable here is omega, so it's going to be e power j omega c t minus e power minus j omega c t. So this I can simplify it further. That is going to be t sine of omega ct divided by pi t. Now that is the inverse Fourier transform or the impulse response of this filter h of omega. So this is h of omega, this h of t, sorry, this h of t, that is t times sine omega ct upon pi t. Now we know h of t and we know what is xp of t. Xp of t is simply the train of impulses. You can see that from here. This is xp of t, and we have just obtained the inverse of this filter, that means h of t. So in Fourier domain, as we are multiplying xp of omega, that means these replicas, with the filter that is h of omega, in time domain it is going to be convolution, just because in Fourier domain multiplication or frequency domain multiplication is going to lead the time domain convolution. So in time domain we have this xp of t and we have just obtained h of t. We simply have to convolve these impulses with h of t. Now what is this h of t? How does it look like? This h of t simply looks like a signal something like this. So this signal, you can see that this signal looks like this. It is having the sine wave appearance that decays with time. So this is what is sine omega ct upon pi t. Now when we are trying to convolve this h of t with xp of t, you may see that if I try to convolve that, we get the result something like this. So you can consider this signal here. Now I am convolving this signal. That means I am convolving this signal at every location of the samples. So this signal is going to be shifted and scaled like this, and the scaling factor is going to be the value of that signal. That means the value of the samples of the signal at that particular location. So overall the picture would be something like this. You can see that here the overall picture is going to be something like this. So here we have one impulse here, another impulse or the sample here, and so on. These samples are getting convolved with this sinc function, and the resultant cumulative effect is going to look something like this. So this sinc functions, or the h of t that we are obtained here, this is a kind of sinc function, is getting convolved with these impulses, and at the end the cumulative effect is simply the addition and the subtraction of these signals. So you can see that the signal is decreasing here and the signal may increase here, so the resultant would be the signal that would look something like this. So you may see that the signal may look something like this. So the envelope, I'm drawing the envelope that you may get by convolving h of t with xp of t, and that's how the signal can be recovered back. So this signal is xr of t, or the recovered signal, reconstructed signal. So we were having these samples of this x of t. You can see that here x of t, and that was sampled, so we were having this xp of t, that means the impulses, and the inverse Fourier transform of this filter was h of t. That was a kind of sinc function appearing something like this. In time domain it is going to convolve, so it is going to be this signal getting convolved with the train of impulses. So you can see that from here. If I show that here, you can see that this sinc function is getting convolved. So we know that any signal, if it is getting convolved with an impulse signal, it is going to give you the same signal but being scaled and shifted by the factor of the value that is present at that instance. So the first sample, if it appears here, there will be the first shift here, the second shift here, third shift here, and so on. With all such shifts and scale version of this sinc function, you are going to obtain a signal that would appear something like this. So it's as good as saying that this sinc function, or the impulse response of the filter, is actually sliding over the samples, and the cumulative effect is going to be something like this. And that's how we are able to recover the gaps in between the samples, and we can reconstruct back the original signal. And that can be done only if the sampling theorem is satisfied. That means the sampling rate is at least twice the maximum frequency, and the cutoff frequency of the filter is between omega m and omega s minus omega m. So now it should be clear that if we are having samples, still we can reconstruct the signal in between if we satisfy the two conditions of the sampling theorem. And that's how the time domain visualization would be. Many times it's not clear that how these samples are getting reconstructed back to the original continuous time signal, and this is how it does. Let's stop here.